Good afternoon, everyone. We'll start the session. So, this is Ankara from the Department of Chemical Engineering, IIT Hyderabad. So, I am the TA for these live sessions. So, we are in the we are having the problem solving sessions for the NPTEL course, Fluidization Engineering. So the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. So already we are into week 11. Just a small change here. Hope I am audible now. So we'll start now. So as I was saying, this is the problem solving session for the NPTEL course Fluidization Engineering. So we are into week 11, and in this week we'll be seeing some more problems related to assignment 11 for this for which the submission is this Wednesday. So I hope you all have been submitting the assignments promptly on time for all these weeks, because as I have been saying every time, the assignments also carry certain weightage in the final exam, final marks. So assignment along with your final exam marks only gives you the final grades or final marks, whatever. So please submit your assignments on time, and I'm sure these problems will be helpful for you people in solving the assignments. If not assignments, it will be helpful for your final exams also, because problem concepts will be similar, however, because we have been seeing the course. So I hope it will be helpful in one way or the other. So we'll start now. So for the course layout, we all are very clear in this as of now, because it is a 12 weeks course, as we have been seeing, and we are almost towards the end. We are into week 11 and we have only one more week left, and apart from that we'll also be having some revision session or something, in which we'll be solving problems which will be helpful for you in the taking the final exams. The revision session will be like gist of whatever we have seen till now, till the last week's class, till week 12, and it will be just your helpful reminder for the revision for the exam. So moving on, we have seen everything in the course, starting from the scratch of what fluidized bed is, to the various phenomena happening inside the bed in terms of bubbling and mixing, segregation. We have seen almost everything, and now we are into mass transfer phenomena happening inside the fluidized bed. So, what is fluidization? We all know now very clearly what fluidization is. It is nothing but in which we pass the fluid inside the bed at a sufficiently high velocity so that the particles start moving and then they behave like a fluid. So we call them as fluidized beds. What are all the advantage in this? We have the increased surface area, so the mass transfer and the heat transfer rates are enhanced because of the increased surface area. So does it mean that we don't have any disadvantage? No, as we have seen in the last week's class also, attrition and loss of material are a few of the well-known disadvantages of fluidized beds. Why do we say disadvantage? Because in certain cases we might need to use costly materials as solids inside the bed. So if there is a loss of those materials, it becomes difficult. And also another aspect is pressure drop is quite high inside the fluidized bed. This makes the usage of fluidized bed to certain extent difficult. Handling of the bed is needs to be careful in the industries. And we can use fluidized beds in various applications for purposes like drying and coating of something over the solids, and also in the reaction engineering aspects we can use it as a we can use the particles as catalyst, and we can pass the fluid and make the reaction happen. So these are all the few areas, and most popularly like FCC catalyst is like a is used by, I mean, application is based on fluidized bed. And later we also see about how solids are characterized, that is classified based on their properties like density and size into four classes by GELDAT A, B, C and D. So, and how these classes behave in differently inside the bed is also we have seen clearly. So moving on, we have also seen about the different regimes of fluidization based on the fluid velocity, I mean fluid inlet velocity, and different ways to calculate the frictional pressure drop. And later we have also seen the solid movement inside the bed in terms of mixing, segregation, staging. All these things we have seen in the last class, and we'll see some more in today's class also. And also we have seen about gas distribution in fluidized bed, how it is important, because in fluidized beds we pass the fluid by using a distributor, which should ensure that the pressure drop is sufficiently fine. And like design of distributor is also there, like we can use porous plate distributor, perforated plate distributor, and nozzle type, tube type. So based on our application and our economical efficiency, the distributor type would be chosen. And later it is about most important thing, bubbling fluidized beds, because why we call it important, because whenever we use the gas as a fluid, bubbles form inside the bed, and we need to be more careful in handling the fluidized beds, because we have additional phase which becomes important, and we need to know and study the bed accordingly. Later we have also seen about the entrainment and elucidation of the solids from the fluidized beds, wherein the solid particles are carried out of the bed. And last it is about attrition mechanism, and finally it is about mass transfer phenomena and the heat transfer phenomena. So the books basically involve Cornell Levens with fluidization engineering, and Geraspo's multiphase flow and fluidization, and Giblaro's fluidization dynamics, and Majumder's hydrodynamics and transport processes of inverse bubbly flows. So we have seen well enough in with regards to books and references. So if you want more detailed analysis of the books and references, I would suggest you to see from the old videos from week 1 and 2 and so on. So it will be given more in-depth analysis. Basically, like fluidization engineering by Kuni and Levenspiel covers almost all aspects regards to fluidization, and it would be very helpful. And followed by Gedaspo's multiphase flow and fluidization, in which the modeling aspects are also covered. So moving on, we have seen in last week the attrition, solid mixing and segregation. And in this week, we'll be seeing about phase dispersion and mass transfer phenomena. I should put here we have moved on to week 11. So yeah, we'll see now. If at any point of time, if there is any disturbance in the video from my end in terms of power cut or power fluctuation, I would request you all guys to stay in the video for some time. I'll rejoin in few minutes. So that's why I made the video open to all. So you can be present without me being present in the video call. So that is one thing. And if there is any internet disruption, please let me know. I mean, if you are facing any delayed response from my end, please let me know. And based on that, I can switch off the video if necessary. But I hope it won't be necessary. So we'll start. So in question 1, now we are into week 11. So we are starting the mass transfer phenomena, and we are into question 1. In question 1, it is asked that when the variation of pressure gradient is dash, the degree of segregation is dash. Oh. When the variation of pressure gradient is dash, the degree of segregation is higher. Option A higher, option B smaller, option C moderate, option D independent. Well, the answer to this particular question is option A higher is the right answer, because constant axial pressure gradient throughout the bed denotes perfect mixing, whereas higher gradient denotes higher segregation. So if there is a gradient, there is a segregation, and if the gradient is higher, the segregation is higher. You can remember it in that way. But if there is a constant axial pressure gradient, the bed denotes thoroughly mixed bed. So when the variation of pressure gradient is higher, the degree of segregation is higher is the right answer. Option A is the right answer. Now we'll go to question 2. In question 2, it is given that the changing composition with bed level of two spherical particles differing in both diameter and density can be determined by means of volume average density, which is expressed as dash. Option A, rho P is equal to C1 rho P1 plus C2 rho P2 divided by rho P1 plus rho P2. Option B, rho P is equal to C1 rho P1 plus C2 rho P2 divided by C1 plus C2. Option C, both A and B. Option D, none of the above. So what is given in the question is that we are asked to find the volume average density formula, and for which we have two compositions of two spherical particles in varying in diameter and density. So density of one particle is rho p1, density of other is rho p2, and based on the concentration it is given. So the answer to this problem is option B is the right answer. Rho p is equal to C1 rho p1 plus C2 rho p2 divided by C1 plus C2. Actually, if you look at the problem itself, I mean option itself, you can understand that we are asked to find the volume average density. So I'll give you a clue of finding the answer. This is not the exact way to do, but just a quick clue. So if you see or if you do the dimensional analysis, you can see that C1 and C1, this both have the same unit. So you will be ending up with the unit of rho P1. Whereas in option A, if you do the dimensional analysis, you will see that you will be ending up with the unit of C. Whereas rho P and C doesn't have the same unit, so option A is wrong. So it can be option A, so option B or option D. And logically it sounds more to option B, so rho P is equal to C1 rho P1 plus C2 rho P2 divided by C1 plus C2 is the answer. So I hope it is clear for you guys. Now we'll go to question 3. In question 3, it is given that the larger particles generally separate to some degree below the smaller. This is due to dash. Option A, size variation is less. Option B, bulk circulation is less. Option C, hydrodynamic uncertainty. Option D, all of the above. So we'll see, we'll look at the options one by one. First, we'll reread the question. It is given that the larger particles generally separate to some degree below the smaller. So when the larger particles separate to some degree below the smaller, what does it mean? Larger particle separation is lower. When does it mean? When the bulk circulation is more, the separation will be low. And size variation is less also, the separation will be low. Here the question generally means that when do we say that segregation is lower? So larger particle is separating very lower and to a very small degree. So if size variation is less, it becomes difficult to separate. So at that case, the separation is less. And in the second case, it is given as bulk circulation is less. Again, this is true because we can see that if bulk circulation is less, it becomes difficult to I think I mentioned one wrong statement in the two statements before. But if bulk circulation is less, it is again becoming difficult. And third one, it is hydrodynamic uncertainty might also be the reason for the lower degree of separation. So all of the above is the right answer. So all of the above is the right answer. Now we'll go to question 4. In question 4, it is given that according to Richardson-Zaki 1954 theory applied for monochromatic bed, where epsilon s is the volume fraction of solids and epsilon s is 1 minus epsilon f, which is the volume fraction of solids, and dl and ds is the binary mixture of spheres of diameters. dl is the diameter of largest sphere, ds is the diameter of smallest sphere, and n is Richardson-Zaki coefficient. So epsilon s is equal to epsilon l into dl by ds to the power of 3 plus m divided by mn. And option B, it is epsilon s is equal to epsilon l into ds by dl to the power of 3 plus m by mn. And option C, it is epsilon s is equal to epsilon l into dl by ds 3 minus to raise to the power of 3 minus m by mn. And option D, it is epsilon s is equal to epsilon l into ds by dl to the power of 3 plus m by mn. So answer is actually option C is the answer. Epsilon s is equal to epsilon l into dl by ds to the power of 3 minus m by mn is the right answer. So here we need to know 3 minus m divided by mn, and also epsilon s is equal to epsilon l into dl by ds. So epsilon is inversely proportional to diameter. Solid packing is inversely proportional to diameter. Diameter is small. Yeah, that is true. Epsilon s is inversely proportional to diameter, and we are raising it to the power of minus 3 minus m divided by mn. So answer is option C. Now we'll go to question 5. Okay, here is an interesting question. We are given segregated solid state in option A and dimensionless density ratio gamma in the option, I mean right hand side. So we are supposed to match left hand side with the right hand side. Now we will see the options. So match the following and okay. Option A, it is A1 B2 C3 D4. Option B, A2 B3 C1 D4. Option C, A2 B4 C3 D1. Option D, A4 B2 C1 D3. So I'll give you guys some time. So please let me know the correct answer. If any one of you would come forward and answer, it would be helpful. Helpful in the sense it would be interesting and interaction would be enhanced rather than me saying the answer. That would be great. Okay, I myself will say. So it is in the left hand side we have different states of segregation. So this one is a completely segregated bed, and this one is perfect mixed bed, and this one is partial segregation, and this one is again partial segregation. So here the segregation is greater than this segregation, and this one is perfectly segregated bed, whereas this one is perfectly mixed bed. So what is that is, if gamma is more, it denotes higher rate of segregation. If dimensionless density ratio is higher, it denotes more segregated. So since complete segregation is given by this, it is 2. That is gamma is greater than 1. I mean greater than 0.1. I think every values are less than this. But if gamma is greater than 0.1, it denotes complete segregation. And next proper segregated one is this one, partial segregation. And for that, we can see that it is here. So it is 0.045 plus or minus 0.015. It is gamma is greater than this value, but it is less than 0.1. So it is coming for option C. And for option B, it is a perfect mixing. So gamma should be very low. So gamma is less than 0.015 plus or minus 0.005. And the partial segregation 2, it has a lower value between 0.015 plus or minus 0.005. It is greater than that, but it is less than 0.045 plus or minus 0.015. So answer is A2 and B 4, C 3, D 1. So answer is option C is the right answer. I hope you are now clear. So how to match this? It is, we are given segregated solid state of bed in the left hand side, and we are given the dimensionless density ratios in the right hand side. So as gamma is higher, it denotes higher segregation. So if gamma is greater than 0.1, it denotes a perfectly segregated bed or complete segregation. And if gamma is less than 0.015 plus or minus 0.005, it denotes perfect mixing. And option C, C and D are different stages of segregation. So here, partial segregated bed. This one is more segregated than this. So this gamma value is greater than this gamma value. So this is less than 0.1 but greater than 0.045. Whereas this is greater than 0.015 but less than 0.045. So that is how we match. Option C is the right answer. So I hope it is clear. The one takeaway from here is that as the beds are more segregated, they have higher dimensionless density ratio. Or if dimensionless density ratio is higher, it denotes higher rate of segregation. So that is this question. And now we'll go to question 6. In question 6 we have, consider a segregation phenomenon for material having two different sizes. And in case large particles are not present in the system, the suspension density is given by dash. We'll read the question again. Consider a segregation phenomena for a material having two different sizes. In case large particles are not present in the system, the suspension density is given by dash. Option A, before that, rho is the liquid density and rho p is the particle density, epsilon s is the volume fraction of smaller particles. And option A, rho bs is equal to rho p into 1 minus epsilon square plus rho into epsilon s. And option B, rho bs is equal to rho p into 1 minus epsilon s plus rho into epsilon s. Option C, rho bs is equal to rho p into 1 minus epsilon s square plus rho into epsilon s square. Option D, rho bs is equal to rho p into 1 minus epsilon s minus rho into epsilon s. So we are having two sizes, smaller size particle and we have larger size particle. So its solid fraction is epsilon s and this solid fraction is epsilon L. And liquid solid fraction is epsilon and its density is rho. And this density is rho s and this density is rho L. So if bulk particles are present, we need to know the density of each and every particle. But what is given, we are considering a segregation phenomena. We are having two size particles. But if larger particles are not present in the system, then the suspension density is given by dash. So larger particles are not present. We have only smaller particles and the liquid density or liquid density only it is given. So it is rho into Just give me a moment. So as I was saying, rho is the liquid density, rho p is the particle density, and epsilon is the volume fraction of smaller particles. And rho bs is equal to rho p into 1 minus epsilon s square, epsilon s the whole square, plus rho into epsilon s. Rho bs is equal to rho p into 1 minus epsilon s plus rho into epsilon s and rho bs is equal to rho p into 1 minus epsilon s square plus rho into epsilon s the whole square, and it is rho p into 1 minus epsilon s minus rho into epsilon s. So answer is option B actually. Rho bs is equal to rho p into 1 minus epsilon s plus rho into epsilon s. That is the answer. So option B is the right answer. We'll go to question 7. In question 7, it is given that the inversion condition is expressed as dash, where UPHS is the segregation velocity of smaller denser particles and U is the velocity. So option A, dUPHS divided by du is equal to 0. Option B, dUPHS divided by du is equal to 1. And option C, dUPHS divided by du is greater than 1. And option C, dUPHS divided by du is less than 1. So answer is actually option A is the right answer. dUPHS by du is equal to 0. At the inversion velocity, the entire bed attains the uniform composition equal to the overall solids composition. So that is the matter. So at the inversion velocity, the entire bed attains the uniform composition equal to that of the overall solids composition. So we say that segregation velocity of the smaller denser particles and the velocity variation is 0. So option A, dUPHS divided by du is equal to 0 is the right answer. And now we'll go to question 8. In question 8 it is given that the dispersion model is represented as dou Ca by dou T is equal to dGV dou square Ca by dou Z square minus U into dou Ca by dou Z. In case a steady flow of tracer gas at a point in a tall narrow fluidized bed is injected, so which of the dispersion model's parameter will become 0 while measuring the upstream diffusion of tracer for the vertical dispersion process? So options are dou Ca by dou T, option B dou Ca dGV into dou square Ca by dou Z square, and option C U, option D none of the above. So just it is actually in case we are given a steady flow of tracer gas at a point in a tall, narrow fluidized bed is injected. So which of the dispersion model's parameter will become 0? So it is a very simple question. Since it is given a steady flow of tracer gas, the concentration variation at with respect to time would be 0. So it is dou Ca by dou T will become 0. Option A is the right answer. Dou Ca by dou T becomes 0. Now we'll go to question 9. In question 9, in case of coarse particles, the tube filled beds have greater impact in dash direction, dash dispersion. Option A vertical, option B horizontal, option C both A and B, option D none of the above. So if tube filled beds, like if internals are present in the bed, and if for the coarser particles the horizontal dispersion will be more affected, because since internals are there, the dispersion in the horizontal direction is the one which will be affected most, and they will have more impact. So option B is the right answer. That is horizontal is the right answer. So I hope this one is clear. If there is any doubt, please let me know. Now we will go to question 10. In question 10, if the concentration is measured in normalized fashion, then the area under the curve for pulse response would be dash. So here in the question itself it is given that it is normalized, and what would be the area under the curve for pulse response. So since it is normalized and it is a pulse curve response, we know it is to be 1. So and looking at the options, option A it is 0, option B 2, option C 1, option D 0.5. So we are asked to find the area under the curve, and if it is a pulse curve and it is a normalized, so area under the curve is 1. Option C is the right answer. So I think it is okay. I mean you're getting the point. So we'll go to question 11. In question 11, actually there are no problematic questions in till question 20. I mean, I think whole session we don't have any problems. So most theory questions, so by now you people are almost familiar with the theoretical aspects of the question, so nothing new will be coming for you guys. So if you are thorough in the theory and you feel you're confident enough, it is okay. Like it will be repetitive for you guys, but yeah, we'll see. We can discuss more if you have any doubts, like any problems, anything, whatever you want, we can discuss. So question 11, the rate of interaction is dash proportional to concentration gradient. Option A directly, option B inversely. So the rate of interaction is proportional to concentration gradient. Option A directly is the right answer, because if concentration gradient is high, the interaction would be high. Can you imagine that, like if concentration gradient is high, so that directly proportional. We'll go to question 12. Just give me a moment, you read the question. The unit of an interchange coefficient KBE is dash. Option A per second per meter. Option B dimensionless. Option C per second square. Option B per second. So just think of the answer. I'll be back in a minute. So answer actually for this particular question, answer is option D. Per second is the answer. We'll go to question 13. In question 13, decrease in bubble size causes dash. Increase in interchange coefficient of bubble cloud. Decrease in interchange coefficient of bubble cloud. No effect on interchange coefficient of bubble cloud. Option D, none of the above. So actually these two are inversely proportional. So decrease in bubble size causes increase in interchange coefficient of bubble cloud is the right answer. So answer is option A. So if you remember the formula, bubble size K, it will come as K into D sphere. So K is inversely proportional to bubble size. So if bubble size decreases, interchange coefficient increases. So that is how it comes. And now we have question 14, in which it is asked that the mass transfer coefficient is directly proportional to dash. Particle diameter, option B, mole fraction of the inert component, option C, diffusion coefficient of the gas, none of the above. So actually it is directly proportional to, mass transfer coefficient is directly proportional to diffusion coefficient of the gas, and it is inversely proportional to particle diameter and mole fraction of the inert component. So it is directly proportional to diffusion coefficient of the gas is the right answer. So that is option C. So it is K into D sphere by D is constant. So it is K is directly proportional to diffusion coefficient of the gas. Now we go to question 15. In question 15 it is asked that based on the kind of gas solid reactions, the rate controlling mechanisms include dash. Option A, gas film diffusion. Option B, pore diffusion. Option C, surface phenomenon. Option D, all of the above. So can anyone say the answer for this question? Answer is all of the above. So based on the kind of gas solid reactions, the rate controlling mechanisms can be any of this. Like it can be gas film diffusion, it can be pore diffusion, or it can be surface phenomenon. Like all these things happen in the gas solid reactions because we have the bubble cloud, everything. So the rate controlling mechanisms can be like gas film diffusion and also the pore diffusion, which is through the particles, and surface phenomena on the surface of the particle or in the surrounding of the particles in the surroundings. So answer is all of the above. Now let us go on to question 16. In question 16 it is given that the Sherwood number is mathematically written as Sherwood number is equal to 2 plus 0.6 into Reynolds number to the power of 0.5 and Schmidt number to the power of 0.33. Consider the particle is exposed to a stationary gas. What will be the Sherwood number? Option A 2.6 and option B it is 2. Option C it is 2.9 and option D it is 0. So what is given? We are given Sherwood number, which is basically written as Sherwood is equal to 2 plus 0.6 into Reynolds number to the power of 0.6 and Sherwood number to the power of, Schmidt number to the power of 0.33. And here it is given the particle is exposed to stationary gas. What will be the Sherwood number? If particle is exposed to stationary gas, what will happen? Reynolds number will become 0 and so the second term becomes 0. So Sherwood number becomes 2. So answer therefore is option B, 2 is the right answer. Now we'll go to question 17. In a homogeneous fluidized bed approach, the mass transfer coefficient between fluidized particles and fluidizing gas is difficult to evaluate due to the complex bubbling behavior and highly uniform hydrodynamic phenomena within a fluidized bed. Option A true, option B false. So you are supposed to answer the homogeneous fluidized bed approach. The mass transfer coefficient between fluidized particles and the fluidizing gas is difficult to evaluate due to the complex bubbling behavior and highly uniform hydrodynamic phenomena within a fluidized bed. Answer is option A true or option B false. So I want you guys to think for a minute and give me the answer, or else like I can give you the answer and I want you to give me the reason. Like you can either tell me or I just take a minute to analyze the situation and have proper explanation. So the answer is actually false. So did you, I hope by now you would have got the explanation. And can anyone say that? Okay, I'll give you. We have two approaches for getting the mass transfer coefficient. One is homogeneous fluidized bed approach and the other one is bubbling bed approach. So in homogeneous fluidized bed approach, we almost treat the bed as a fixed bed. Only in those conditions, homogeneous fluidized bed approach should be effective and those assumptions would be effective. In case of fixed bed, it we do not have the complex bubbling behavior, or we do not have highly uniform hydrodynamic phenomena. So these things won't happen, so the answer is false. In homogeneous fluidized bed approach, the mass transfer coefficient between the fluidized particles and the fluidized gas is difficult to evaluate due to the complex bubbling behavior and highly uniform hydrodynamic phenomena happening within the bed. The answer is actually false. Why? Because the approach homogeneous fluidized bed uses the assumption of fixed bed, and only in case of fixed bed we can evaluate. Other than that, in case of bubbling bed, we use bubbling bed approach. I hope it is clear. Now we'll go to question 18. In question 18, we have the cloud phase and the emulsion phase are considered to be perfectly mixed. Thus, which of the following conditions justify aforesaid? where Ca is the concentration of A in the gas stream and Cai is the concentration of A at the gas particle interface. So Ca is the concentration of A in the gas stream and Cai is the concentration of A at the gas particle interface and Cae is at the emulsion phase. So the cloud phase and the emulsion phase are considered to be perfectly mixed. So under that condition, which of the following conditions justify the aforesaid? Have Ca is the concentration of A in the gas stream and Cai is the concentration of A at the gas particle interface. Option A, Cai is equal to Cae and option B, Cai is equal to Cac and option C, Cae is equal to Cac and option D, all of the above. And the right answer is actually all of the above is the answer because Cai is the concentration of gas at the gas particle interface and Cae is at the emulsion. Similarly, C is the cloud phase and here E and C. So at the interface, at the cloud phase, at the emulsion phase, all are same because it is the perfectly mixed bed. The cloud phase and the emulsion phase are considered to be perfectly mixed. Thus, which of the following conditions justify the aforesaid? And C is the concentration of A in the gas stream and Cai is the concentration of the particle at the concentration of A at the gas particle interface and E and C denotes the emulsion phase and the cloud phase respectively. And because it is considered as perfectly mixed, Cai is equal to Cae, that is interface is equal to emulsion and interface is equal to cloud, also emulsion is equal to cloud. So answer is all of the above is the right answer. All of the above is the right answer. Now we will go to question 19. In question 19, consider KGB as transfer of component A from the particle phase to the bubble phase in a fluidized bed via zones with transfer from particles dispersed in the bubble phase and transfer of gas across the bubble cloud boundary. In case the system has non-absorbing and non-porous particles, what will be the correlation of KGB with the interchanging coefficient between the bubble and cloud? So I repeat, consider KGB as the transfer of component A from the particle phase to the bubble phase, that is KGB is from particle phase to bubble phase in a fluidized bed via transfer from particles dispersed in the bubble phase and transfer of gas from the bubble cloud boundary. So it is from particle to the bubble phase and so it is particle to the bubble and the cloud. In case the system has non-absorbing and non-porous particles, what will be the correlation of KGB with the interchanging coefficient between bubble and cloud? So here the particle is non-absorbing and also non-porous. So what will be the relation between KGB and KBC? So option A, KGB is equal to KBC. Option B, KGB is equal to 2 times of KBC. And option C, KGB is equal to 0.5 times KBC. Option D, KGB equal to 1 KBC. So here we need to note two things. First one, it is given that the particle is non-absorbing and second one, it is mentioned that the particle is non-porous. So answer is option A is the right answer because KGB is the transfer of component A from particle to the bubble phase and KBC is from the bubble phase to the cloud phase. And since the particle is not absorbing, it both remains the same. Option A is the right answer. So we'll go to question 20. In question 20, it is given that in the grid region, an additional mass transfer can take place due to the dash flow of gas through the interface of them forming bubbles. So in the grid region, an additional mass transfer can take place due to the dash flow of gas through the interface of them forming bubbles. Option A conductive, option B convective, option C both A and B, option D none of the above. So it is given that it is in the grid region. So additional mass transfer can take place due to the dash flow of gas through the interface of them forming bubbles. So actually it is convective flow of gas, it is not conductive. So we all know that, but still because of the convective flow of gas, additional mass transfer can take place, and this is in the grid region. So answer is option B is the right answer, that is convective is the right answer. So answer is option B. Option B is the right answer. So now actually we have covered the questions from week 11. So these 20 problems will, I hope, will be helpful for you guys when you are solving the assignments. So now we are going to see week 10 assignment problems, and we have 15 more problems, and again all of these are theory based questions, so it won't take much time. So since time is now 4:02, I would like to take a small break, and we can meet at 4:07, and we'll come back with question. We'll start with week 10 then. Now actually we'll take a 4 minutes break. Time already is 4:03. Just a small break. coming back, we have 1 minute left. So I just tell random things, I guess. Do you remember like what we have seen last week? It is about attrition and those things. So we'll start there. Like we have seen attrition, solid mixing and segregation, those type of questions we have seen in the last class. And so today we are going to see some problems from there also, like just an extension. So it is week 10 and question 1 we have. Choose the correct expression for the overall attrition rate. Option A, RAO, that is overall attrition rate, is equal to minus W bed into dWL divided by dt. And oh, okay. Why did it go here suddenly? What was I saying? It was about overall attrition rate. RAO is equal to minus W bed into dWL by dt. W bed is the weight of the particles in the bed, and is the dWL is the elutrated solids weight. D is equal to RAO is equal to 1 by W bed into dWL by dt. Option C, it is RAO is equal to minus 1 by W bed into dWL by dt. And option D, none of the above. So answer is actually option C is the right answer, because overall attrition rate is equal to change in the weight of the bed and due to the change in the elutrated solids with respect to time. So it is minus 1 by W bed into D into WEL divided by dt is the right answer. So answer is option C. Now we'll go to question 2. In question 2, it is given that attrition of the particles in the fluidized bed reactor is because of dash. Option A, only surface wear. Option B, only fragmentation. Option C, both options A and B are correct. Option D, none of the above. So, why do you think is attrition happening inside the bed? Is it because of only surface wear, or it is also because of fragmentation? So attrition is the damage of the particles and breaking down of particles, and it can happen actually due to two reasons. The first one is the surface wear. Due to constant rubbing of particles against each other, the surface wear happens, and small material loss from particles happens over time. And the second one is fragmentation. Fragmentation, when due to the impact of the particles, it can break down and the particles might get cracked into 2 or 3 fragments, and that is known as fragmentation. So attrition can actually happen due to surface wear, or it can happen due to fragmentation. So answer is option A and B is the right answer. That is option C. Both options A and B are correct. Now we will go to question 3. Over here we have, which one of the following is true about Rittinger's theory? So we have 3 theories: Rittinger's theory, Kick's theory and Bond's theory, which are concerned with the particle breakdown and new surfaces getting formed. We deal these theories in the comminution, and we have option A, the energy required is proportional to the length of crack initiating breakage. Option B, energy consumed is proportional to area of new surfaces formed. Option B, energy required to bring analogous changes is proportional to the volume of these bodies. Option D, none of the above. Actually, it is area of new surfaces created. That is area of new surfaces formed. Rittinger's theory is about energy consumed is proportional to the area of new surfaces formed. So we will deal with the other two theories in the next question actually, like the formula. So but for now, Rittinger's theory is proportional. Rittinger's theory states that energy consumed is directly proportional to the area of the new surfaces formed. So now we have a question wherein we are asked to match the correct one. So we have different combination theories in the left hand side and the corresponding formula in the right hand side. So the first one is Rittinger's surface theory, and second one is Bond's theory, and third one is Kick's theory. And in the right hand side we have E is equal to C into 1 by x2 plus 1 by x1, and QE is equal to 2 times of C into 1 by root of x2 minus 1 by root of x1, and RE is equal to minus ln of x2 by x1, and SE is equal to C into 1 by x2 minus 1 by x1. So the answer is actually, we look at the options once. Option A, 1P 2Q 3R. Option B, 1S 2R 3Q. Option C, 1Q 2S and 3R. Option D, 1S 2Q and 3R. Answer is actually option D is the answer. Okay, D. Option D is the right answer. I'm sorry. Option D is the right answer. Rittinger's theory, as we all know, it is new surfaces formed. So S E is equal to C into 1 by x2 minus 1 by x1. And Bond's theory, it is about I think it is about cracks formed. So it is 2 into C into 1 by root of x2 minus 1 by root of x1. And Kick's theory, it is E is equal to minus ln of x2 by x1. Okay, Kick's theory actually states that the communication energy depends on the reduction ratio and it is independent of original size of field. So remember that way, Kick's theory, it is like it is independent of the original size, rather it is dependent on the size ratio, reduction size ratio. Therefore, we are having E is equal to minus ln of x2 by x1. And Rittinger's surface theory, it states that energy required for the size reduction is directly proportional to new surfaces formed, new surface area created. So it is E is equal to 1 by x2 minus 1 by x1 into C. And then we have Bond's theory. It states that the work required to form particles of size is proportional to the square root of the volume surface ratio. So here it is, Bond's theory is 1 by root of x2 minus 1 by root of x1 into 2 into C. So we'll repeat once again. Rettinger's theory is actually proportional to the new surfaces formed, and Bond's theory states that it is proportional to the square root of the surface area of the particles, surface area to the volume ratio of the particles, and therefore it is 1 by root of x. It is proportional to, and Kick's theory, it is proportional to the reduction size ratio, and it is independent of the original size. So if you remember that way, it will be easier. Rittinger's surface theory. So it is new surfaces formed. So it is 1 by x. And whereas Bond's is it is proportional to square root. Kick's is like depending on the size reduction ratio. How can you guys remember Kick's? Make some anagrams or something, and remember somehow. Kicks is proportional, it is stating of size reduction ratio, and Bonds, it is of square root, and Rittinger's surface theory. Rittinger's, I guess it is easier to remember because it is surface theory, and therefore it is based on the new surface created. So answer is actually option D, 1s, 2q, 3r. 1s, 2q, 3r. Okay, now we'll go to question 5. In question 5, choose the correct option. Again, it is a match, and we have option 1, bubble induced attrition. Option left hand side we have cyclone driven attrition, and last one, jet induced attrition. And in the right hand side we have 4 options. Option 1, it is function of jet penetration length, and option Q, it is due to force exerted by the cyclone on the particles, and R, it is due to the high velocity interparticle collision, and S, it is due to low velocity interparticle collision. So we have option A, 1R, 2Q, 3P, option B, 1S, 2R, 3Q, option C, 1S, 2Q, 3P, option D, 1Q, 2S, and 3R. So the right answer is actually 1S, 2Q, 3 and P. 3P. So we all know the easy thing is like cyclone driven attrition. It is due to the forces exerted by the cyclone on the particles, and jet induced attrition is actually a function of jet penetration length. And the left out one is bubble induced attrition, and it is due to the low velocity interparticle collision. So we'll look at the answer first before discussing further. So answer is option C is the right answer, 1S, 2Q and 3P. So just give me a moment. So actually attrition modeling, three sources that contributes to attrition. Based on that only we model attrition rates. So first one is actually the bubble induced attrition, as we see is it is caused from the low velocity interparticle collisions. So answer is option S. 1S. And bubble second one is cyclone driven attrition. It is caused by the forces exerted by the cyclones on the particles. And third one is the jet induced attrition. It is a function of jet penetration length. It occurs at a certain volume above the gas distributor. So which is the function of jet penetration length? So actually jet induced attrition, it occurs at a certain volume above the gas distributor, and this height above the distributor is given by the jet penetration length. And there are various variables in this particular model, like number of orifice holes, gas flow rate, gas velocity, and nozzle diameter, orifice velocity, etc. So if there is no interaction between the individual jets, the entire rate of attrition in that particular jet region can be accounted from only summing the contribution of that each jet. That is, if there is no interaction between the individual jets, the entire rate of attrition in the jet region can be obtained by summing the contribution to that of each jet. So the jet induced attrition is actually RA distributor is equal to NOR into RAJ, where RAJ is function of rho GOR and DOR square UORN. The proportionality factor depends on the properties of the solid material. The attrition rate per jet is proportional to the square of the orifice diameter, and so on happens. Bubble induced attrition, on the other hand, is caused from the low velocity interparticle collisions, and momentum exchange therefore is not high enough to break the final particles, break it to final particles. So bubble induced attrition is described by relative production rate of fine particles as RA bubble is equal to 1 by W bed into dWEL into bubble, dWEL bubble by dt. W bed is the instantaneous bed mass, and WL bulb is the mass of fine particles which is produced by bubble induced attrition. This is similar to the overall attrition rate which we have seen. So instead of overall attrition, WL is the fine particles produced by the bubble induced attrition. And lastly we have cyclone induced attrition. Cyclone induced attrition is nothing but where forces exert attrition is caused by the forces exerted by the cyclone on the particles. These forces lead to impact and rubbing on the inner wall of the cyclones, and these particles break and attrition phenomena happens, and the change of the particle size distribution also occurs. So that is what is cyclone driven attrition. Now I think it is clear. Bubble induced attrition is nothing but due to the low velocity interparticle collisions, and cyclone driven attrition, it is due to the force exerted by the cyclone on these particles. And jet induced attrition is actually occurs at a certain height above the distributor, which is a function of jet penetration length. So answer is 1s 2q3p. 1s 2q3p. So answer is option C. Now we are going to question 6. We have choose the correct option regarding the breakage probability of material during attrition. The breakage probability of the material is a strong function of dash. Option A, cyclone inlet gas velocity. Option B, particle concentration and its size. Option C, material specific constant. Option D, all of the above. So answer is actually all of the above is the answer. Option D, all of the above is the answer. So how it is about breakage probability of the material during attrition. So the breakage model actually is used to predict the change in the particle size distribution of the material that undergoes stress in the gas cyclone, and actually depends on four factors. The first one is the cyclone gas inlet gas velocity, so option A is true. And second one is particle solids load and particle size, so particle concentration and its size, 2 and 3 factors. And the last one is a material specific constant, so option C is also right. So all of the above is the right answer. This model is only due to the particle wall collision, breakage occurring due to the particle wall collision. Breakage model. So breakage probability of a material during collision is due to cyclone inlet gas velocity, particle concentration and its size, and material specific constant. And it is used for the particle wall collision alone. So now we will go to question 7. In question 7, the dispersion model reasonably represents the vertical mixing in tall beds in which rather small scale mixing takes place. Select the correct expression for the dispersion model. Option A, dou CTP divided by dou T is equal to dSP into dou square CTP by dou Z square plus US into dou CTP by dou Z. And option B, dou CTP by dou T is equal to dSP into dou square CTP by dou Z square minus US into dou square CTP by dou Z square. And dou CTP is divided by, dou CTP by dou T is equal to dSP into dou square CTP by dou Z square and minus US into dou CTP by dou Z. Option C, it is option D, it is dou CTP by dou T equal to US into dou square CTP by dou Z square plus dSP into dou CTP by dou Z. Option A, option C. Both are similar except the change of sign. So here we need to know dispersion model is nothing but dou C by dou T equal to D into dou square C by dou Z square plus U into dou CP by dou Z. So here it is we are using dispersion model. So we can see that only option A or option C can suit the dispersion model according to the equation. Option D is equation wise it is wrong. Similarly, option C is also wrong. So answer is actually option C is the answer. Dispersion model reasonably represents the vertical mixing in tall beds in which rather small scale mixing takes place. So here it is vertical mixing, so it is dSP. So dou CTP by dou T variation with respect to time equal to dispersion coefficient into dou square C by dou Z square minus US into dou CP by dou CTP by dou Z. So answer is option C. By looking at the equations, we can arrive at 1, and that answer dispersion model is equal to dou CTP by dou T is equal to dSP into dou square CTP by dou Z square minus US into dou CTP by dou Z is the right answer, which is option C is the right answer. Now we are going to question 8. In question 8, it is given that for a completely mixed stirred tank reactor, the residence time distribution can be expressed by the following expression, where TR denotes the mean residence time of the particles, and we are asked to find the residence time distribution. So option A, it is RT is equal to TR bar exponential of minus T by TR bar. Option B, R of T is equal to 1 by TR bar into exponential of T by TR bar. And option C, it is RT is equal to 1 by TR bar into ln of minus T by TR bar. And option D, it is RT is equal to 1 by TR bar into exponential of minus T by TR bar. So the answer is actually option D. R of t is equal to 1 by TR bar into exponential of minus T by TR bar. So here TR bar denotes the mean residence time of the particles and RT is the residence time distribution, and residence time distribution is equal to 1 by TR bar into exponential of minus T by TR bar. So answer is option D is the right answer. Now let us go on to question 9. I think a similar question. Residence time distribution for a system with n stages of fluidized beds reactor of equal size can be calculated as dash. R of t is equal to 1 by 1 minus n factorial into t factorial ti bar into 1 by ti into exponential of t by ti bar. Option B, R of t equal to 1 by 1 minus n factorial into t bar equal to 1 by ti bar into exponential of minus t by ti bar. Option C, R of t equal to 1 by 1 plus n factorial into ti bar into 1 by ti bar into exponential of minus t by ti bar. Option D, it is R of t is equal to 1 by 1 minus n factorial ti bar square into 1 by ti bar into exponential of minus t by ti bar. So answer is actually option B is the answer. R of t residence time distribution for a system with n stages of fluidized bed reactor of equal size can be calculated as, this is 1 by ti bar into exponential of minus t by ti is the residence time distribution in a one case. So here it is 1 by 1 minus n factorial into ti bar. So that alone comes extra, but other than that, this expression, original expression remains. So answer is option B is the right answer. Option B, R of t is equal to 1 by 1 minus n factorial into ti factorial, ti into 1 by ti into exponential of minus t by ti is the answer. T bar is the mean residence time of the fluid. So it is the volume of void space in the bed divided by volumetric feed rate of gas gives the T bar. So yeah, now we'll go to question 10. In 10th question, it is given that solid mixing index is defined as the ratio of mass fraction of gypsum in the top portion of the bed to the gypsum mass fraction in a perfect mixed bed. Select the correct answer regarding the solids mixing index M. So this question we have seen in the last week. It's a similar question, not exactly the same. So here M denotes the mixing index, solids mixing index. It is defined as a ratio of the mass fraction of gypsum in the top portion of the bed and divided by the mass fraction of gypsum in the perfectly mixed bed. So, if M is equal to 1, option A, we are asked to identify what M signifies. M is equal to 1 indicates complete mixing. Option B, M is equal to 0 indicates complete segregation. Option C, both options A and B are correct. Option D, M is equal to 0 indicates complete mixing. So, first we'll see what M signifies. M is the ratio of gypsum in the top portion of the bed to the ratio of, to the gypsum mass fraction in the perfectly mixed bed. So, if the bed is perfectly mixed, the mass fraction of gypsum in the top portion would be equal to the mass fraction of the gypsum in the perfectly mixed bed. So, that means that M is 1 for a complete mixed bed, right? So MS1 indicates complete mixing, that A is true. Second one, what is given, M is equal to 0 indicates complete segregation. What it means, M0? M0 means the numerator is 0. Numerator 0 meaning mass fraction of gypsum in the top portion of the bed is 0. So what is gypsum actually? Gypsum is the particles whose sinks to the bed, and flotsam is the particle which floats to the top of the bed. So, during segregation, if we speak in that aspect, so if the material which has a property to sink is not present in the top portion of the bed, it means that it is completely segregated. All those material has come to the bottom of the bed. So M is equal to 0 indicates complete segregation. Again, this is true. So option C, both options A and B are correct, is again true. So option D, M is equal to 0 indicates complete mixing, is false. So answer is actually option C is the right answer. Both options A and B are correct, is the right answer. Now we will see question 11. In question 11, we have segregation index S defines the intensity of particle separation in the bed. Choose the correct statement regarding the segregation index where XSF denotes the flotsam mass fraction in a perfect mixed bed. So what is segregation index? Segregation index is given by S, and it is the ratio of mass fraction of flotsam in the top portion of the bed to the mass fraction of flotsam in a perfect mixed bed. And XSF denotes the flotsam mass fraction in a perfect mixed bed. So here we are again given the options and we need to identify that. Remember that in the mixing index gypsum comes and in the segregation index flotsam comes. Other than that, the formula remains the same. In mixing index, it is the mass fraction of gypsum in the top portion of the bed divided by the mass fraction of flotsam in the completely mixed bed. And here it is segregation index, it is mass fraction of flotsam in the top portion of the bed divided by the mass fraction of flotsam in a perfect mixed bed. So first one, it is x is equal to 1 by x is, sorry, s equal to 1 divided by x. Sf denotes the stage of complete segregation. Is this true? So coming back to the formula, in a complete segregated bed, flotsam will be at the top of the bed and gypsum will be at the bottom of the bed. So S denotes mass fraction of flotsam in the top portion of the bed divided by the flotsam in the mass fraction of flotsam in a complete mixed bed. So XSF is the flotsam mass fraction in a perfect mixed bed. So it is mass fraction of flotsam in the top of the bed divided by XSF. That is S. So in a segregated state, flotsam will be at the top. So mass fraction is 1. So it is S is equal to 1 divided by XSF, denote a state of complete segregation. So option A, it is 1, S is equal to 1 by XSF, denotes a state of complete segregation. That is true. Option B, S is equal to 1 denotes a state of perfect mixing. Again, this is true. If the bed is perfectly mixed, flotsam mass fraction in the top of the bed will be equal to the flotsam mass fraction in a perfect mixed bed. So it ratio becomes S is equal to XSF divided by XSF. So it becomes 1. So again this is 1. S is equal to 1 denotes a state of perfect mixing, means true. Option C, both options A and B are correct. Again this is true. Option D, none of the above. So answer is therefore option C is the right answer. Now we are going to question 12. In question 12, the changing composition with the bed level of two spherical particles species differing in both diameter and density can be determined using volume average density rho p. The volume average density can be represented by the following expression. Option A, rho p is equal to C1 rho p1 plus C2 rho p2 divided by rho p1 plus rho p2. Option B, rho p is equal to C1 rho p1 plus C2 rho p2 divided by C1 plus C2. Option C, rho p is equal to C1 rho p2 plus C2 rho p1 divided by C1 plus C2. Option D, rho p is equal to C2 rho p1 plus C1 rho p2 plus C1 by C1 plus C1 plus C1. So we all know the answer to this question because we have seen the question in the previous content. I mean, in the first part of the lecture today, we have seen the answer to this. So the right answer is actually option B is the right answer. Rho p is equal to C1 into rho p1 plus C2 into rho p2 divided by C1 plus C2. We have seen the explanation there. So now we are going to move on to the next question, that is question 13. Choose the correct option for bed suspension density where rho p, rho epsilon s, epsilon l denote the particle density, liquid density, volume fraction of small particles and volume fraction of large particles respectively. In the absence of smaller particles, we are asked to match actually. So in the left hand side we are given in the absence of smaller particles and in the absence of larger particles. So in the right hand side we are given rho bs is equal to rho p into 1 minus epsilon s plus rho into epsilon s. Q rho bl is equal to rho p into 1 minus epsilon l plus rho into epsilon l. R rho bl is equal to rho p into 1 minus epsilon l plus rho p into epsilon l. And yes, rho bs is equal to rho p into 1 minus epsilon s plus rho p into epsilon s. So first we'll see and we'll then go to options. First one, in the left hand side it is given in the absence of smaller particles. In the absence of smaller particles, we will be left with only larger particles. So suspension density is given by rho bl. So it must be either Q or R. So looking at the options we have, rho p into 1 minus epsilon l plus rho into epsilon l is the right answer. Here it is given rho p in the right hand side. Second option also, which is false. So 1 Q, and in the absence of larger particles, then only smaller particle remains. So it is rho bs. Rho bs is therefore given by rho p into 1 minus epsilon s plus rho s. Again here rho p is given, which is false. So actually we can eliminate r and s and we can match only with p and q. So in the absence of smaller particles, only larger particle remains, and rho bl is equal to rho p into 1 minus epsilon l. Epsilon ls is the volume fraction of the larger particles plus rho into epsilon l. And second one, in the absence of larger particles, rho bs is equal to rho p into 1 minus epsilon s plus rho into epsilon s. So 1 q, 2 p P is the right answer. We look at the options now. Option A 1R 2Q. Option B 1S 2R. Option C 1Q 2P. Option D 1P 2Q. So what is the answer? The answer is 1Q 2P is the right answer. So accordingly, option C is the right one. 1Q 2P is the right answer. 1Q 2P. Now we will go on to question 14. In question 14 we have, as per Richardson-Zaki 1954, the voidage is epsilon for the monocomponents bed is represented by dash. Again, these questions we have seen in the first part of today's class. So this is just a repetitive, I guess. But still we'll see the answer. Option A, epsilon s is equal to epsilon L into ds by dl into 3 minus to the power of 3 minus m by mn. Option B, epsilon s equal to epsilon L into dl by ds into to the power of 3 minus m by mn. Option C, epsilon s is equal to epsilon L into dl by ds to the power of mn by 3 minus m. Option D, epsilon s is equal to epsilon L into dl by ds to the power of 3 plus m by mn. So, answer, as we have seen, epsilon is inversely proportional to D. So epsilon s is equal to epsilon L into, it should come as dl by ds. So straight away we can eliminate option A, and answer is to the power of 3 minus m by divided by m into n is the right answer. So answer is option B is the right answer. Option B is the right answer. So now we will go on to question 15. And that is the last question for today's session. In question 15 we have that, choose the wrong answer regarding attrition. We are asked to choose the wrong answer. Remember that we are not asked to choose the correct one here. So we are asked to choose the wrong one. So the first one is that spray dried crystals are allergic to attrition. Option B, for the same type of particles but of different sizes, the fractional loss due to attrition is larger for smaller particles. Option C, smaller particles are more difficult to break than larger ones. Option D, none of the above. Option D, none of the above is the right answer. Spray dried crystals are allergic to attrition. but for the same type of particles but with different sizes, when we are taking into consideration the particle size distribution for the same material, the fractional loss is, due to attrition is larger for the smaller particles. But smaller particles in general are more difficult to break than the larger ones. So these things are covered in the particle shape, size and its distribution uh, in the factors affecting attrition. So please, there are so many factors affecting attrition. So in exam point of view and your knowledge point of view, please be aware of all those factors affecting the attrition. So that's it for today's session actually. I thank you for attending today's session. The time now is actually 4:53. So if you have any doubts, please let me know. We can discuss. If not, we can close the session. So as a quick revision, in today's class we have seen uh, 20 problems from week 11 and 15 problems from week 10. So in the first part of the session, we have seen how mass transfer phenomena happens in the system and also the interchange coefficients. All those things we have seen in the first part of the session. And in the second part of the session, it is more about attrition and solids mixing, segregation and attrition. And second, in the first one, we have seen of the phase dispersion and the mass transfer phenomena. So I think it is mostly we have seen only the theory aspects in today's class. There was no problem in today's session. So yeah, so I think it is straightforward. So yeah, so that's it for today's session. So please let me know if you have any queries. We can discuss or else we can leave the session. So I'll wait for 2-3 minutes and then we can leave. Okay, thanks for today's session. I'm closing now.